So as our second speaker, we have Professor Raquel Urtasun speaking about interpretable neural motion planning. Raquel is a professor of computer science at the University of Toronto and a co-founder of the Vector Institute for AI. Her work spans many areas of AI, including vision, robotics, machine learning, and language. And in particular, she's been at the very forefront of vision-based autonomous driving research for almost a decade now, including a recent stint as chief scientist at Uber ATG. She has won numerous awards from NSERC, the Canadian Ministry of Education, NVIDIA, Google, Amazon, and 2 Best Paper runner-up prizes. She's also the founder and CEO of Wabi Innovation, an autonomous vehicle startup. So without further ado, let me hand you over to Professor Urtasun.
Yes, thanks for having me here. It's really exciting. Cool. So hopefully you can all see my screen.
Yes.
Yeah, fantastic. Great. So yeah, today I'm going to be talking about interpretable neural motion planning, which is one of my favorite topics, I guess, in self-driving. And in particular, I want to maybe motivate why there is a need for new autonomy systems. So if you look at the evolution of self-driving over the past 17 years since the first DARPA challenge, we've seen meaningful progress, but if you look at commercial deployment, it's really limited to very small operation domains that are also very simple. So there is a lot that needs to be done still in terms of developing algorithms that, on one side, we can really solve the long tail of all the events and things that might happen as you drive. This is one of the big challenges as it relates to autonomy, which is basically building the brain of the self-driving vehicle. The second big open challenge, which is oftentimes less talked about, is do we have the right tools, capabilities in order to test our self-driving vehicles? And there is so the answer to this is no. So there is a need for really real-time high-fidelity closed-loop simulators that would really enable safely test at the scale of all these rare events in a way that is computationally feasible, but at the same time has a right level of fidelity, so that things correlate perfectly as you see in the simulator as what will have happened in the real world. So in my opinion, these are the 2 big open questions or directions of self-driving. Can we build the autonomy system that can actually generalize to all the scenarios, geographies, etc.? And second, can we actually build a testing system that can also be used to train this autonomy system in a way that is scalable and has high fidelity? So today I will be talking about the autonomy system alone, but there is plenty of very interesting work that we've done in the past and we are doing right now in terms of the simulator. Now, since there is some new things as well happening recently, I also want to give a hint about what we are doing with this new company, Wabi, which I guess was founded now around 4 months ago, something like this, and we came out of stealth mode a couple of weeks ago, and it was very excited to finally tell everybody what we were doing after we decided to leave Uber. So in particular, if you look at these 2 fundamental open questions, as I say, testing as well as autonomy. So Wabi is building fundamental new technology of how to address these 2 problems. On one side, for autonomy, we're building an AI-first approach, meaning that we want to unleash the full power of AI in a way that is still interpretable, is end-to-end trainable, and verifiable, and can really solve complex tasks and all these long tail events. So generalizes really well. So that's one of the technological sort of breakthroughs that we are doing. The second one is a lot of emphasis on simulation and building this closed loop simulator with an unprecedented level of fidelity, where you can really test at the scale the software stack. And in terms of what are the use cases that we are tackling, we're going to start with long haul tracking. Which makes a lot of sense in terms of commercial deployment, right? Driving on a highway is easier than driving on cities, right? So in my opinion, this is where you will see this technology making sense from a commercial perspective. Now, trucks are more difficult than cars as well. So it's not that everything is easier, but it's definitely where is the deployment first. And then we're building general technology that would expand to other use cases such as ride sharing, last mile delivery, etc. Cool. And as I mentioned, we launched it last month. It was, it was very well received, very exciting. We also announced our first round of financing, so we went directly to Series A with 100 million Canadian dollars raise. Cool. So last slide on Wabi. We are hiring. Very excited. If you want to really look at self-driving with new lens, with an AI lens, with a lens of innovation at the core of a company, this is the place for you. So ping me afterwards. Plenty. We have more than 30 openings right now, so we're hiring massively in both Toronto as well as San Francisco. Cool. Now let's go back to the the topic of the workshop, and I said I was going to talk about autonomy. So in order to do so, let me tell you a little bit about how autonomy, how to try to solve autonomy, or the kind of approaches that people have been developing for this. So on one side, you have what they call the traditional software stack, which is basically 99% of what you will see in industry. And this is a very modular approach. So it works as follows, right? So you sense the environment. This is shown here with the LiDAR seen from the top, right? And the first thing that all these vehicles do is that you localize with precision of a few centimeters, right? And the idea is that you want to do this not just because you want to route from point A to point B, right? But more importantly, because you want to utilize your high definition maps that tell you a lot about the environment before you even see it. And this is very, very useful for motion planning, for example. Then once you localize, basically the perception system is going to perceive the world around you. Then you need to predict where the different actors are going to be going in the next few seconds. And this is also referred to motion forecasting in computer vision. Then you basically need to look around you and plan a safe maneuver that will drive you towards your goal in a way that is comfortable and safe. Okay, and you repeat this process every fraction of a second. Now, I'm really simplifying here in the sense that every one of these models, if you look at the commercial software stack, it has hundreds of models within the models. Okay. Now, what are the advantages of such an approach, right? So it's interpretable. We have these intermediate representations such as bounding boxes, trajectories that we know how to interpret and we know how to potentially validate as well. And it's also very easy to incorporate prior knowledge, right, on top of these representations. For example, if you want the motion planner to adhere or satisfy rules of traffic. Now, there is also a few disadvantages that are really hindering progress of this approach. One is that, as I mentioned, I have a very simplified version here. In reality, this is a massive sort of modular approach. And then you end up, having hundreds and hundreds of engineers, typically even more than 1,000 in some of the top companies, working on this one product, one software stack, right? So what you end up doing is that, you have perception engineers that maybe are actually targeted only with tracking of this specific category. So they don't really understand the entire picture, but they are focused on this one model. And so you have this development happening in silos, and it's very, it's very hard, it's impossible, right, to come up with the right architecture for everything if you have this view of this minuscule subpiece that someone needs to piece into this large system. So this lack of this holistic view. Also, you have small interfaces because a lot of this is hand design. So maybe you have bounding boxes, maybe some covariance estimate of your noise, but by that point you have already lost all the information, right? So as a consequence, you're going to have these cascading errors that they propagate through the software stack. And in general, developer productivity is actually really low, right? You have this massive system, it's a single system, you have hundreds to thousands of people working on this. Every time that you change something, everything else is going to change the, the performance, and there is no real automation. So you need to change one thing at a time. And so every single little change actually takes, a quarter or more to actually land in production. Okay, so this together makes, the progress in self-driving to be very, very slow. The alternative is, for those that believe in AI like a religion, right, is that, oh, I can just use, my favorite neural net and it's going to basically solve the task for me. Right? And the idea is that it's very simple, right? It's a single, it's a couple of lines of code that is basically your, your neural net. So that's an advantage. And it's trained for the end task, right? You typically train it for basically the steering command acceleration. So every time that you improve your metrics, you're going to improve the task of driving. This is actually in contraposition to the modular approach, where maybe your perception system gets better, but your system level metrics do not. And that's also one of the things that make progress very, very slow. Now, one of the problems with this is that, well, first of all, in order for this to really generalize, etc., it's going to need a lot of examples. And when I say a lot, I really mean a lot, right? So it's going to need to observe traffic-like things, traffic accidents and things like this in order to be able to handle those. And that's, potentially unethical, right? And if you're going to collect this kind of data with your sensor configuration. So doesn't scale well, and also it's really hard to incorporate prior knowledge. This is a black box kind of AI system, right? And also for validation and safety, it's also very hard to do something here, right? So some pros, but no, there is also some big cons here. So what we've been building over the past, several years is, well, there's actually a different line of thinking, which is something that lies in between these two approaches, right? They're very extreme. So we can build something that is still modular, but at the same time is end-to-end trainable, right? And have the advantages of automation and really training the entire system for the end task, right? And have much better developer productivity without leaving out, the interpretability, the verification piece as well. So this kind of hybrid approach is what we've been calling, interpretable neural motion planners. And the idea is that, as is end-to-end interpretable, right, you can actually use more complex functions. You can even use, raw sensor data for your motion planning, right? So you don't have these cascading errors. And you don't need to also forget about everything that has been done in the field, but you can inspire the way that you build the system with, some of the great progress of things in motion planning, etc., that have been built so far. Okay, but the idea is that you have full automation in terms of, it's still end-to-end trainable the entire software stack. Okay, and as you have also shared computation between these models, then you actually have lower reaction times. So it's actually simpler, not more difficult to do real-time inference here. Cool. So, in the remainder of the talk, I'm going to tell you a little bit about some of the generations of this kind of technology that we built. I'm going to very quickly, briefly talk about the first generation that we built, 3.5 years ago now. And then I will be talking about, two of the latest generations. So the first generation was actually pretty simple, right? And now I want you all to think about solving self-driving with an AI, neural net kind of perspective. Okay, so let's try to turn our minds to this. So one very simple way to do this is to treat the problem as a multitask learning problem. Okay, meaning that you want to have a single network that is going to do many tasks, and the many tasks are going to be detection, prediction, as well as motion planning. Okay, so in order to do this, so how do we do this? So very simply, we're going to have some representation for our sensors. In this case, it's illustrated with data. You can have multiple sensors, right? There is also a lot of fusion approaches that we developed in the past. You also need, obviously, to have map information, right? For the motion planner is important. And then basically you process this data through, a neural network that is going to create some intermediate representations from which through an output header, you're going to detect the objects of interest. You're going to regress where they're going to be in the next few seconds. And on top of this, the way that we're going to do motion planning is relatively similar to what sometimes called path time algorithm is, where we're going to generate a cost volume, and this cost basically is going to represent what is the cost for the self-driving car to be at any point in time in the planning horizon and at any location, such that planning will be very simply we will sample trajectories that are physically possible. We are going to evaluate all these trajectories by indexing this cost volume that is actually non-parametric, is learned through the neural net. And then planning is nothing by selecting the trajectory that has the minimum cost. Okay, so if you look at this, typically, if you put here a hand engineer cost, this would be like the part-time kind of algorithm. Okay, so you can still inspire yourself with this, more classical algorithms, but have a fully learned approach. So this is actually, something that you can learn with only a few examples of, driving as well as bounding boxes. And let me show you what it does in a video. Okay, so in here, you're gonna see our detections, the predictions into the future, illustrated in this case is 3 seconds with these dots, which are half a second into the future. And then this cost volume is 3-dimensional, so it's difficult to show. So I'm gonna project it to 2 dimensions. Time is gonna be different colors, and I'm only gonna show you areas of low cost. Okay, so for you to visualize what the vehicle is thinking about potential paths that I could take, right? And then through your sampling, you basically select the best trajectory. Okay, so you can incorporate behaviors, things like this through sampling. Okay, so you see that is multimodal, right? The cost volume by definition, which is great. You don't need to have a fixed number of modes or anything like this, and it can handle very complex maneuvers like you see here, like super notches, changing lanes, etc., which are typically pretty difficult to do in motion planning. Okay. So this was, our first attempt to build an end-to-end system, still kind of interpretable. Being able to have, to plan with a high degree of capabilities. Now, if you look at this particular way of doing, end-to-end motion planning, it has one potential problem as it relates to safety, and it's not just about this interpretable neuromotion planner, but it's about any approach that uses detection as the basis for perception for self-driving. Okay, and what is the problem is that if let's illustrate this with a scenario. So here I have my self-driving car, and I have 2 cars in the scene. If I detect, these 2 vehicles and I predict something reasonable, basically my motion planner, right, is going to tell me to slow down. Okay, and I'm going to do the right thing. However, if you rely your perception stack on detection only, the problem is that detection has a threshold in, right, operation, meaning that something that is below the threshold, you're going to just ignore. Right, so, and this very well will have, potentially will have been discarded. Right, so what happens in that case is that if you have a detection-based perception, right, is that suddenly you're blind, you don't see this guy, right? So your motion planner is going to say, oh, I want to accelerate, and you're going to enter a collision. And maybe once it comes to actually have, be above the confidence threshold, maybe it is inevitable for you to not collide, right? You will collide with the vehicle. Right, so for safety, yes, basing your self-driving vehicle on just a perception system that uses only detection is problematic, okay? Because of this threshold in operation. And this is always the case also for online maps if you use a threshold in operation, things like this. So what's the alternative? Right, so the alternative that we're going to see is maybe we can just get rid of detection altogether, right? And then think a little bit about the requirements for perception with a motion planning less. Okay, so what does that mean is that typically the way that detection is used in motion planning is that things are rasterized, and then you build cost functions based on those rasterizations. Right, so the question is, why do I need to detect with a threshold and then rasterize and then do something else? Can I just predict a semantic occupancy in the first place? And this semantic occupancy will have all the, we have the notion of uncertainty already encoded into it, and I don't need to, threshold or eliminate anything. Basically, I can utilize, all my predictions without having a computational problem, which is why we threshold typically the detections. Okay. All right. So what we're going to do now is we're going to switch, change this motion planner in 2 ways. This interpretable neural motion planner in 2 ways. We're going to predict this very different intermediate representation, that is these occupancies, and then the motion planner itself, instead of relying on something fully learned that only has prior knowledge in the loss function, here what we're going to do is we are going to have also some a combination of learned things and handcraft things such that we can ensure safety. Okay. All right. So let's see how to do this. So in terms of the occupancies, right? So now you can go a little bit wild into what this represents. So what are the things that you will be interested as a self-driving car to know? Well, different classes, right? So and what is interesting here is that different classes are not necessarily mutually exclusive. Why? Because I can have bikes on a bike rack on top of a vehicle. I can have a person riding a bike, right? Or I can have a person in a vehicle that I might see, right? So we're going to have these different occupancies, as I say, at the level of the subcategories are not going to be mutually exclusive. And then I'm going to have for every one of these subcategories, then mutually exclusive subcategories. Okay. And what are these going to be? Well, things that you might want to use for your motion planner, right? The notion of occlusion is very important, right? You would like to understand whether something is occluded because you don't see well and probably you want to slow down, right? It's important as well to understand who is on your route, who is on incoming traffic or a conflicted lane, etc., right? So that you can do pretty sophisticated motion planning maneuvers based on this information, right? And the way to actually get these occupancies is also very simple. You can do it end-to-end, right? Where we are changing a little bit the basic architecture here, but don't pay too much attention there. But the idea is that we have a recurrent net now that for the planning horizon is gonna predict basically the semantic occupancy into the future for this planning horizon. Okay, so we're gonna do perception and prediction in a single step by unrolling this recurrent net. Okay, and then time here is the horizon or the prediction horizon time. Cool. And as I said, then for the motion planner, we can have something where we have a combination of the learn features as well as more handcraft features. But what we really like these sampling-based planners because they're very amenable to learning and you can do a lot of great things with them. So the idea again is going to sample trajectories. We're going to evaluate these trajectories with some cost, and we will pick the one with the minimum cost. Okay. So what are these? So the way that you sample trajectories is important. So we do in this case map aware, and it's behavior aware. Okay. So you can have samples that are all, you can execute them, and they're all pretty great, right? And the goal of the planner is just to select one of those. And in terms of evaluation trajectories, we will have again a learnable. This is end-to-end learn everything, okay? But it's a learnable set of costs where we will incorporate some of our prior knowledge. For example, that we want to avoid occupied regions. This is fully learned, right? We want to, sorry about that. We want to drive comfortably. We want to follow the route, not go on a different path. We want to drive, closer to the center because it's safer, etc., etc. Okay, so you can build a whole bunch of costs this way. And as I said, you basically select the one with the minimum cost with a very simple operation. All these operations can be done on GPUs. Okay, so you can do this super, super fast. Cool. So this is also end-to-end trainable. Basically, we have some cross-entropy laws for the semantic occupancy, and we have max margin laws. Think of the max margin planning, right, as the loss function in terms of the planning piece as well. Cool. Sorry, my computer is doing something. Then one thing to note is that actually this works much better than either the handcraft planner itself with the using the latest prediction systems, for example, like the Waymo prediction system here, or using behavioral cloning or very simple planners like adaptive cruise control, or even the previous planner that I showed you. Okay, so in terms of collisions, it's much safer. It's also much better in terms of things like jerk. You have the same progress and it's closer to the human. Okay, so it has all the advantages. And doing end-to-end training is better than stage-wise. This is because you want the intermediate representations to be adjusted to the specific planner. This is one of the reasons why doing neuromotion planners is important. And this is just showing the representation that if you use these occupancies, it's much better than if you use this detection followed by the trajectories, okay, within this and having the same motion planner. Okay, so you see there is quite a big difference, particularly in collisions and safety between the two. Cool. So let me show you some illustrations of open loop results. Open loop meaning that we're going to observe 1 second and we're going to make predictions into the future, and I'm going to show you the plan maneuver if we will have executed the entire maneuver. Although this is not really what you do in practice as you have this in a real system. Okay, that is for you to understand, what this, our plans in this horizon, how good or bad they are. Okay. And different colors here are going to represent the occupancies of the different semantics. All right, so let me show you this. Displays. Thing to note is that it's very multimodal, right? Like this bus could have taken a right turn or could have continued straight. You have the right semantics, right? And everything is predicted directly in terms of this occupancy. Things that are interesting to see is that it's also able to do like very precise predictions. Like pedestrians are very tiny, right, in these occupancies, but it still predicts them well, and it predicts that this vehicle is going to stop for the pedestrians to pass. Okay, so it's not going to collide with pedestrians. So you can have fairly sophisticated behaviors with this kind of representation. Cool. So I show you open loop metrics, but it's very important to not just stop in open loop, is to show closed loop metrics. Okay, meaning that you're going to execute the plan that you intended to do, and then the world is going to change with respect to your execution. Okay, so this is what we need, this closed loop simulator. And in this case, because we want to test the entire software stack, we need a closed loop simulator that is able to simulate the sensors. Okay, so very quickly, I'm going to tell you how we can build such a system, and then I will show you results. Okay, so we're going to take a maybe 5 minutes break to go into simulation for a second. Cool. So what do we need in order? Yeah.
I just wanted to quickly interrupt to say we have about maybe 2 minutes, including 3 minutes, including questions, I think.
Oh, wow. Okay.
Yeah.
Cool. So maybe I show you only a bit of the simulation.
Okay.
and I will not show you the last motion panel. Sorry. I guess I'm talking too much today. Cool. I always get too excited. Great. So the 3 pieces that you need for simulation, you need to be able to basically recreate the entire world, right? That you want to simulate, generate the behaviors, right, in a way that everybody reacts to each other, and then be able to simulate the sensors. Okay. So typically in the industry, this is done by artists. Creating the virtual worlds is done by artists manually generating this. So what we do instead is that we can recreate everything that we have observed just by driving around the world. This is the static part of the environment, as well as all the different assets that you might have seen. This is every single vehicle that we observe as we drive, and every single pedestrian that we observe as we drive. And for pedestrians, we can actually estimate also them in a way that we can reanimate them with their formations later on to do any activity we want. Then you can generate the scenarios. We can do this also automatically with AI, and then we can simulate the behaviors. And let me show you some of the simulations. So this is our multi-agent AI simulator that is simulating everybody together, and yes, in different geographies in terms of the maps. And then you can see that it's generating behaviors that are actually very, very realistic. And in particular, I'm going to show you some of the long tails. Hopefully. What is this? Maybe it's the next step. Yeah, so some of the long tails of behaviors, for example, generates like really nice matches. And simulation, this is like almost learning how to drive, right? Because you have to simulate how everybody drives in the same scene in a way that is realistic. You see U-turns, lane changes, and the last thing I'm going to show you is protected laps, which are difficult to simulate. And you see here, this is fully automatic. There is no scripting that you will see in this procedural stuff that the industry uses. Cool. So you have the behaviors, and the last thing is that you simulate how the sensors observe the scene. In this case, this is the data simulator, which is takes only a few milliseconds. And on the left-hand side is the simulator. On the right-hand side is the real data. And you see that in green is the output of the perception system. In this case, it behaves the same in both simulation as well. And if this thing wants to load, you're going to see here a safety critical case. Thank you. And then the simulation here. So this is, we are fully putting all this together to simulate, particular scenario we're interested in. And this is the sensors, and then here the vehicle is reacting by having this as input. Okay, so you can really test the entire software stack. and then you can do this at scale. Okay. And then basically you can simulate more sensors in a way that is compatible in 3D. In this case, we are inserting fake objects. In per video, there is 3 to 5 objects that are fake vehicles, and the question to you is, can you find which ones are? If my computer wants to show you this. And thank you. Anyways, so this vehicle here is fake, this vehicle here is fake. But it's super realistic, it's in 3D, it has shadows, and the behaviors are also very realistic. Okay, cool. So we can put all this together and then look at the metrics. Basically, we see that by doing this new version of, this new semantic occupancies and end-to-end training, you further see much bigger gains. Okay, that if you do the, perception followed, perception followed by prediction followed by motion planning, you end up with a much more unsafe planning. Okay. This is why it's very, very important that you actually test this thing in simulation. Cool. So I'm going to skip the beautiful new motion planner. Instead, yes, conclude. So I show you 2 instead of 3 bullets, right? I show you the first version, which is the motion planner of how to take processor data with a fully learned approach. And then I show you how to, these dense representations are really good for increased safety. And the thing I didn't show you is our new version of motion planner that actually doesn't even require high definition maps. Thank you for your attention. This is all, and I'm happy to answer any questions if you have.
Thank you very much, Raquel. That was a really interesting talk. While we are waiting for audience questions to pipe up, maybe let me ask you one question. The last bit where you showed us the simulated multi-agent driving, where you acquired it from, I think, just offline data collected of real highways, right? So I'm curious there about to what extent you're able to simulate the response of other agents in the scene to odd behaviors that your motion planner might sample, right? Things that might not necessarily have easily been observed in the data, where, when you're beginning to plan your motions, you might say that I'm going to plan from a wide range of possible motion trajectories, and some of those trajectories are behaviors that might not necessarily exist in the real world. And to what extent are we basically able to treat this as an interventional simulator, where other agents can actually respond to some weird movement that your ego car makes and say that, okay, this is bad?
Yeah, I think there is 2 things here, right? One thing is, can your simulator simulate behaviors that are on the long tail side of things? And if you, learn the simulator with log likelihood, it's not going to be able to do so unless you sample until the end of the world. Right? So you need to do something special. And the other question, which I think is more of what you're asking, is because a prediction system is nothing but a simulator of what's going to happen and rolling into the future, right? Whether your prediction system can actually simulate those rare events such that the motion planner can actually take them into account. So although the prediction system and the simulator are similar tasks, they are different. So I'm going to answer you in terms of the prediction system. So I didn't show it here, but the way that we handle this is by with a different type of model that and basically adding, so it's a latent variable model that really captures the relation between all the different agents and the diversity of the sampling. So we learn the diversity of the sampling process, such as our diverse samples are in terms of motion planning behavior. So sampling these behaviors of how I want to enroll my prediction system such that they will make my motion planner behave differently. And if you can do this efficiently, which with this is a technique that I guess is under submission now, but you can read on archive, which we call lookout, then you can actually very efficiently get all those rollouts for all these rare events and then take them into account in your motion planner.
Right. Yeah.
Hopefully I gave you the gist of how this works.
Yeah. Thank you. let's see. So I see a question in the audience from Jason Ma. How robust is the sampling-based planner to the relative weighting among the cost functions?
So the sampler is independent of the cost. Okay, and what is important for the sample is that first, they are executable maneuvers. Otherwise, you are going to need to have an additional planner that smooths trajectories at the end and does other things. And the second one is that you really want coverage. You want to make sure that you evaluate all the possible maneuvers in the event that actually there is some emergency. Okay. Now, I guess the question is, what about the cost? Your costs, are there? Is there a combination of costs sufficient for all the difficult maneuvers that you need to do? And the answer here is actually, this is why it's very important to learn this end-to-end and to have very sophisticated cost functions. It typically is a linear combination of costs that every cost looks at one thing. Go in the middle, go this, do that. Okay, but if you have the ability to learn end-to-end, then you can combine this in much more sophisticated ways and learn very complex functions. And then you can do all the sophisticated reasoning. Okay, so that's the next generation that maybe I will show you next year from what Wabi has. Okay, but great question as well.
Great. Thanks, Raquel. I think that's more or less all that we have time for.